Hello, aloha, sawadika, and mabuhay. Good day, students. How are you today? I know that you are all very eager to learn our new lesson. I am your Sir Jeffrey Kadungog, your teacher broadcaster in Mathematics 10 for Quarter 3 of Week 2. I am sure that you are all very excited. So let's get started. Today, we shall be talking about permutations. Are you ready? So, if I may ask, what's your idea on this topic? Well, if there is none, you don't have to worry about that because we shall be discussing it intensively today for you to really understand what this lesson, which is once again about permutation. Our lesson, by the way, for today is based on the most essential learning competency of the Department of Education, which is to solve problems involving permutations. So, what are we waiting for? Let us start. So break a leg and let's all bring it on. Our learning objective for today are the following. First, we have to be able to illustrate the permutations of objects. And second of all, we are going to solve problems involving permutations. So, at the onset of our discussion, it is necessary for us to have the definitions first. So for our definition, permutation is simply an arrangement of objects in a specific order. And once we say specific order, order and arrangement matters. Again, when we speak of permutation, order and arrangement does matter. So for you to be able to understand that, let us have some examples. First, how many ways can you arrange 3 people for a picture? Once again, let me read that for you. How many ways can you arrange 3 people for a picture? You have to take note that you are using all 3 people. So the answer would be, do you have your answer in mind now? Before I'm going to reveal the answer, let us imagine 3 blanks. Now, these 3 blanks represent the arrangement of these 3 people for that picture. For the first blank, we have 3 available persons to be in that position. For the second blank, we only now have 2 since the first blank has been occupied by 1 already, or it has been taken by 1 already. And for the last blank, consequently, we only have 1 for the same reason. Therefore, our answer would be 3 times 2 times 1. And what do we have now? Voila, it's a simple number 6. Therefore, there are 6 possible ways or number of ways by which we can arrange 3 people for a picture. Remember the term factorial in our previous lesson? Okay, so the factorial, this is the same as when we are going to use a factorial. Let me just reiterate for you what the formula or what the notation is for a factorial. So n factorial is basically equal to n times the quantity of n minus 1 times the quantity of n minus 2 and so on. And using the previous example, for us to be able to use the factorial notation, this would simply mean 3 factorial is equal to 3 times the quantity of 3 minus 1 times the quantity of 3 minus 2. Now we are going to bring that down. 3 factorial is equal to 3 times 2 times 1, and that is equal to the same answer as we had answered a while ago, equal to 6. To really know more about what permutation is all about, let us have another example. Suppose a business owner has a choice of 5 locations to establish his or her business. he or she decides to rank them from best to least according to some criteria. Now, how many different ways can he or she rank them all? Our answer would be, using the factorial notation, is 5 factorial equals 5 times 4 times 3 times 2 times 1. And that is equal to 120 ways. So our answer would be, there are 120 different ways for her or him to rank those 5 locations. Note that he or she ranked all of them. But what if he or she decides to rank only the top 3? How would then our answer change? So our answer would simply be 5 times 4 times 3 equals 60. Now this is no longer a factorial problem simply because you don't rank all of them. We only get to use the top 3. Now this leads us to the permutation rule. We have it here. The permutation of n objects taken r at a time is simply equal to n factorial over the quantity of n minus r factorial. Now you might be wondering what is n and r are. So where n is simply the total number of objects or total number of ways, while your r is the number of available positions to be filled. So this is simply read as n objects taken r at a time. I'm gonna say it again, n objects taken r at a time. So remember the businesswoman who only wanted to rank the top 3 out of 5 places, our problem a while ago? So this is actually a permutation problem. We get to say that 5 times 4 times 3 is equal to 60. Now let us use the permutation rule for that. The permutation of 5 objects taken r at a time is equal to 5 factorial over the quantity of 5 minus 3 factorial, that is equal to 5 factorial over 2 factorial, equals 5 factorial is equal to 120 over 2 factorial is equal to 2. So dividing 120 by 2, we get the answer to be 60. Notice that we have the same answer. Another problem is, a TV news director wishes to use 3 news stories on the evening shows. She wants the top 3 news stories out of 8 possible news stories. The question is, how many ways can the program be set up? So the solution would be, the permutation of 8 objects taken 3 at a time is equal to 336. The full solution will now be Now, let us now move on to another problem. How many ways can a chairperson and an assistant be selected for a project if there are 7 scientists available? The answer, as well as the solution, would be the permutation of 7 objects taken 2 at a time is equal to, yes, got it right, 42. And for the full solution of that problem, we have, so then we will be able to say that a factorial is also a permutation. Let us try to learn more about that by using the problem. How many ways can 4 books be arranged on a shelf? You can do 4 factorial, or you can set it up as a permutation. So it's either 4 factorial or you will be using this solution. The permutation of 4 objects taken 4 at a time is equal to 24. And for the full solution to this problem, here it is. So then we have to be reminded and ponder about the following, or we have to take note that 0 factorial is equal to 1, and we also have 1 factorial is equal to 1. Once again, 0 factorial and 1 factorial are both equal to 1. Why is that so? You can actually research it on your own for the proof. Why is it that 0 factorial and 1 factorial are both equal to 1? So this leads us to a special permutation when letters must repeat. So if we have an example that involves letters, like this. How many permutations of the word seem, spells S-E-E-M, can be made? Since there are 4 letters, the total possible ways is 4 factorial, right? If each letter E is labeled differently. Also, there are 2 factorial ways to permute E1 and E2. I'm referring to the 2 E's in the word seem. But since they are indistinguishable, these duplicates must be eliminated by dividing by 2 factorial. How is that so? So when we say how many permutations of the word seem can be made, we can have our answer as simply 4 factorial all over 1 factorial times 2 factorial times 1 factorial. Ever wonder what this 1 factorial, 2 factorial, and 1 factorial are for? Well, in the denominator, you get to see that there is a 1 factorial. That first 1 factorial is actually for the letter S. Now that 2 factorial is actually for the 2 E's, and the other 1 factorial is for the letter M. So, we can actually just simply don't mind about the 1 factorial because they can only be simplified to 1, by the way. So, we are only left with our solution to be 4 factorial over 2 factorial, and that is equal to 12. And for the full solution, we have it here. Now, this leads us to another permutation rule when some things repeat, may it be letters, what have you. So, on your screen, you get to have a seemingly complicated formula or rule, but it actually is just going to be read as the number of permutations of n objects in which K1 are alike, K2 are alike, etc. Or you can have it in your mind as simply the permutations of n objects taken r at a time is equal to n factorial all over k sub 1 factorial times k sub 2 factorial times k sub 3 factorial, and so on up to k sub p factorial. For example, find the permutations of the word Mississippi. Okay, Mississippi is actually a place in the United States, and you get to notice that there are letters that repeat in the word Mississippi. So here is the breakdown of those letters. The number of letters, we have 11 as the total number of letters for the word Mississippi. We only have 1 for letter M, 4 for letter I, another 4 for letter S, and we have 2 for the letter P. So our solution would now be 11 factorial, that calls for the total number of letters in the word Mississippi, divided by the quantity of 1 factorial, that's for the letter M, times 4 factorial, which is for the letter I, times another 4 factorial for the letter S, times 2 factorial for the letter P. And when we answer that, we get to have 34,650. Again, 34,650 is the answer. You can eliminate the 1 factorials simply because they are just but equal to 1. Let us try to examine more examples pertaining to permutations by which we can actually use the factorial notation. So here is the first example. How many 4 different codes can be made from the digits 0, 3, 6, and 8? So for our solution, the permutation of 4 objects taken 4 at a time is actually equal to 4 factorial. And this 4 factorial is equal to 4 times 3 times 2 times 1. And so therefore, our answer would be 24. The second example would be, how many ways can you arrange the letters in the word equal? Spells E, Q, U, A, L. So for our solution then, we get to see that the word equal has 5 different letters. So we can use the formula, the permutation of n objects taken n at a time, where your r is actually equal to your n, and that is equal to n factorial. So the permutation of 5 objects taken 5 at a time is equal to 5 factorial. And we know that 5 factorial is actually equal to 5 times 4 times 3 times 2 and times 1. And the answer would be 120. So let us have more example. In how many ways can 6 mannequins be arranged in a showroom? Once again, in how many ways can 6 mannequins be arranged in a showroom? Our solution then would be, the formula to be used is the permutation of n objects taken n at a time, where n is actually equal to your r, is equal to n factorial. This can be used in solving such situation that we just have made mention of. So, the permutation of 6 objects taken 6 at a time is equal to 6 factorial. And we know that for sure, 6 factorial is equal to 6 times 5 times 4 times 3 times 2 times 1. And guess what? The answer is 720. You got it right. And let us have more example. Another is, in how many ways can 7 persons arrange themselves in a row for picture taking? I will repeat, in how many ways can 7 persons arrange themselves in a row for picture taking? So the same formula or notation to be used. The permutation of 7 objects taken 7 at a time is equal to 7 factorial. And we know that 7 factorial is equal to 7 times 6 times 5 times 4 times 3 times 2 times 1. And that is equal to, this time, a whopping 5,040. 5040. This type of permutation is otherwise known as the distinguishable permutations. Some other references that you may have encountered in your own researches and personal studies would tell us that it is a permutation of a set of objects where some of them are alike. And then sometimes we get to see different kinds of formulas. This time, let us take note of this formula. The number of distinguishable permutations of n objects when p are alike, q are alike, r are alike, and so on is given by p is equal to n factorial all over p factorial times q factorial times r factorial, and so on. In this particular notation, we get to see that a while ago, we used k sub 1, and this time we use p. A while ago, we used k sub 2, and this time we used q. And a while ago, we used k sub 3, and this time we use r. There's no problem about that because they all mean the same. So let us have more examples for this particular type of permutation, which is the distinguishable permutations. Example: how many distinguishable permutations are possible with all the letters of the word calculator? Calculator is something that we most of the time use, especially in these kinds of problems. So the solution would be, there are 10 letters in the word calculator. C, A, L, C, U, L, A, T, O, R. There you go, 10 letters. So our solution would now be N is equal to 10. Our P is actually equal to 2. And why is it 2? Because your P represents the total number of letter C. And in the word calculator, we get to see that there are 2 letter C's. Now what about for your Q? Your Q now would be equal to 2. And this time around, this 2 denotes that of the letter A. There are 2 letter A's in the word calculator. And finally, for your letter R, that is also equal to 2, because this time around, it represents, or it is for the letter L. And in the word calculator, we get to see that there are 2 letter L's. So, using the formula, we have the permutation is equal to 10 factorial all over 2 factorial times 2 factorial times another 2 factorial. And you see that 10 factorial is equal to 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So 10 factorial is equal to a whopping and sizzling 3,628,800. You got it? Very good. What about for the denominator? The denominator are all 2 factorials. And you know for a fact that 2 factorial is just 2 times 1. And 2 times 1 is equal to 2. So all you have to do is to multiply 2 3 times. So 2 times 2 times 2. And you will get 8 for sure. So the solution would now be 3,628,800 divided by 8. Can you now give me your answer? Now, if your answer is 453,600 ways, then you are close to being a genius. Very good. 453,600 is our answer. Want some more? Okay. The librarian asks you to arrange the books on a shelf. There are 5 identical math books, 7 identical science books, and 4 identical English books. This time the question is, in how many ways can you arrange them? So our solution would be, since there are a total of 16 books, therefore, N is equal to 16. How did we get 16 in the first place? 5 for mathematics books plus 7 for science books, that makes 12. Plus 4 for English books, and that makes 16. So, what will be the values of our P, Q, and R this time? P, we can denote that as the mathematics books, the number of mathematics books, so that gives us 5. Q is for science books, so we have 7. And consequently, we have R equals 4 for English books. So, the equation or the solution would now be 16 factorial all over 5 factorial times 7 factorial times 4 factorial. Now, 16 factorial is equal to 16 times 15 times 14 times 13 and so on. But we can actually end up with just 7 factorial. So 16 times 15 times 14 times 13 times 12 times 11 times 10 times 9 times 8 times 7 factorial. Why is that so? Why is it no longer necessary for us to continue 7 times 6 times 5 times 4 times 3 times 2 times 1? That is precisely because we see a 7 factorial in the denominator. So all we need to do is to cancel that 7 factorial in the numerator and that 7 factorial found in the denominator. We know for a fact that 120 is equal to 5 factorial and 4 factorial is equal to 24. And in the numerator, we see 12 times 10. And you know that 12 times 10 is equal to 120. So we may also cancel out 12 and 10 found in the numerator and the 5 factorial down below. So all we are left with is the 24 now in the denominator and the numbers 16, 15, 14, 13, 11, 9, and 8 in the numerator, which when all together multiplied will give us the product of 34,594,560. Okay, divide that with what is left in the denominator, which is 24, and that gives us our final answer, which is 1,441,440. Wow, that was quite exhausting. I wish that that could have been our money. That might be of great help in the pandemic we are all experiencing today. Now, it's time for us to discuss a new kind, not really new kind, but another kind of permutation, which is quite related to your previous lesson, all about circles. So what I'm saying is, we shall now be talking about circular permutations. Now, what are these circular permutations all about? Circular permutations, put simply, is just the number of permutations of n objects arranged in a circle. And this is expressed as P is equal to the quantity of n minus 1 factorial. Once again, the permutation for circular permutation is equal to the quantity of n minus 1 factorial. So, let us try to use such formula in these following examples. Example 1. In how many ways can 6 choir members be seated around a circular table with 6 chairs? So our solution would be P is equal to the quantity of n minus 1 factorial. Substituting 6 for n, the equation now becomes P is equal to the quantity of 6 minus 1 factorial. And it's very easy to get 6 minus 1. We are all sure that to be equal to 5. And since we still have our factorial notation outside, so that is just 5 factorial when simplified. And it is equal to, very good, 120. You want some more examples? Here it is. In how many ways can 8 kids be seated in a merry-go-round if 2 kids insist to sit beside each other? I'll say it again. In how many ways can 8 kids be seated in a merry-go-round if 2 kids insist to sit beside each other? Event 1. Event 1 would mean, suppose Kid A and Kid B insist to sit beside each other. Therefore, they are taken as 1. So, instead of n to be equal to 8, we will be having n now to be equal to 7. So, using the formula for circular permutation and the quantity of n minus 1 factorial, when substituted with 7, so P is equal to 7 minus 1 factorial. 7 minus 1 is equal to 6, and P now is equal to 6 factorial. 6 factorial is equal to 6 times 5 times 4 times 3 times 2 times 1. And there you go. Our answer is 720. But that isn't the correct answer yet. We have another event 2 to consider. Event 2 this time would mean that the two kids can actually be arranged in two ways. AB or BA. Right? Because they can interchange seats with each other, although they are taken as one. This means that we still have to multiply 720, our previous answer, by 2. So, the correct and final answer for this kind of problem would be 1,440 ways. So there are 1,440 ways by which 8 kids be seated in a merry-go-round wherein 2 kids insist on sitting beside each other. So, that concludes our discussion for today. I hope and I am very optimistic that you have learned something about our lesson for today, which is permutations. This has been your Sir Jeffrey Kadungog. I am your teacher broadcaster in Mathematics 10. I am from Santa Ana National High School, saying, always remember to stay at home and let's all continue to preserve life. Thank you very much and have a good day.